Sustainability, decarbonization, and economic opportunity in a transitional period. Hello, everyone. Welcome to the Society of Vacuum Coaters TechCon 2021 Virtual Symposium. My name is Marc Landry. I'm a master research technician, engineer, jack of all trades, designing and building custom vacuum deposition systems for solar R&D for over 35 years. For the last 28 years of my career, I've been at NREL, the National Renewable Energy Labs, part of the U.S. National Lab Consortium located in Golden, Colorado. NREL is the preeminent lab in the world for renewable energy research of all types, the NASA of renewable energy. We do it all: photovoltaics, wind, biofuels, genetic engineering, hydrogen storage, fuel cells, batteries, energy and grid analysis, energy systems and grid modeling, pretty much the whole gamut. NREL also funds a lot of university research as well as collaborative research with industry. The mission of the lab is, and has always been, to push the technologies, reduce the cost of renewables by either finding ways to make them faster and cheaper, and also by making them more efficient and way less carbon intensive. Why? Why did we spend billions in research over the last 43 years? Reality. The human race needs to decarbonize. We've all thrived in the age of fossil fuels. Too much, as a matter of fact, as our populations have grown to unsustainable levels, meaning there are just not enough resources to provide a basic standard of living without destroying our environment. That's it in a nutshell. Alas, the devil is always in the details. The definition of sustainability. First, let's define sustainability. Population growth is out of control. The world, with its 7.8 billion people and ever increasing, is heading toward a precipice at a rapidly increasing rate. CO2 in the atmosphere, mercury in our water, and more stress on food production uses enormous amounts of water and resources. The human race is running out of room on the environmental, economic, and societal credit cards. Al Bartlett, Professor Emeritus of Physics from the University of Colorado, spent the last 30 years of his career preaching about sustainability and the problems with exponential growth of society. I saw him speak at NREL about 25 years ago, and back then he didn't paint a pretty picture of the future unless we all work together to solve these problems. His lectures are on the web. Go look them up. They changed my whole worldview. Anyways, he said it best. He called it the first law of sustainability. Quote, population growth and or growth in the rates of consumption and resources cannot be sustained. The key word being growth. Quote, sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. What humanity does today is kick the can down the road for future generations to deal with, as we all live beyond our environmental means. No one on earth is living in a bubble. We know what the problems are. We are currently in a huge hole and, quote, when you find yourself in a hole, the best thing to do is stop digging. The human race rapidly needs to decarbonize. Collectively, we've thrived in the age of fossil fuels. Our population pendulum has swung to the wrong side of sustainability, having grown to unsustainable levels, creating havoc for generations yet to come. We now constantly hear about or personally witness the issues related to climate change as a result of ever-increasing CO2 emissions. Here's where most of that CO2 comes from. Industry. Concrete. Concrete, the second most used material on Earth besides water, accounts for about 10 to 12% of all the CO2 emitted worldwide every year. The world produces enough concrete to build a New York City about every 3 or 4 weeks. 35 billion tons of concrete every year. concrete emissions of CO2 is almost 1-to-1. 1 ton of concrete equals 1 ton of CO2. Not an easy solution there. Maybe carbon capture and sequestration, but that adds a huge and uncompetitive cost. So it will take some time to find a lower carbon source for such a ubiquitous building material. But it has to be done. The smart people are working on it. Opportunities for innovation. Steel, which is now being made cost competitively using hydrogen instead of coke as a reducing medium for making iron and steel. Sweden has the first commercial scale steel plant using this method that will help transition to this innovative and economically viable technology. Agriculture. It takes a lot of fossil fuels, 3.5 barrels of oil per cow, both for machinery and transportation, as well as enormous quantities of nitrogen and ammonia-based fertilizers, almost all made from oil and natural gas derivatives. This is another hard one, so it might take a while to reduce the carbon footprint of agriculture. Ground transportation. We use liquid fuels, specifically oil and its derivatives, as our primary energy source for locomotion. Cars, ships, trains, jets. Oil and gas are volatile commodities, and as such are subject to economic shocks and price fluctuations. Not good for the average Joe or Jill like me or you. Solutions are on the near horizon. Would you have ever believed that GM, as well as all the other major auto companies around the world, would set a goal of 2035 or earlier to be out of the internal combustion engine business and switch to all electric and fuel cell vehicles? Our transportation sector can be decarbonized relatively quickly and economically, as long as we have lots of carbon-free electricity and a modern grid system to allow it all to work. Aviation. What about aviation? We'll still need energy-dense liquid-based jet fuel, for a while anyway, but a change is coming. During this transition period, liquid hydrocarbon jet fuels can now be made from biomass cost effectively. Richard Branson of Virgin Airways fame has invested $3 billion of his own money on a biofuels plant for his airline. He was sick of the price volatility of jet fuel and wants his company to move into the future. A company called Gevo is now producing jet fuel using renewable electricity and CO2 from the air. I recently read an article about a startup company in Boulder, Colorado, designing superconductor wiring systems for commercial aviation. Why, you ask? Even jet fuel will become obsolete, as these new generation of commercial aircraft will use electric ducted fan engines with extremely reliable, high power, high efficiency electric motors powered by lightweight fuel cells on board, fueled by energy-dense liquid hydrogen generated from excess renewable capacity in off-peak hours. These will be deployed on large 200 to 300 passenger aircraft. Electricity generation and distribution. This is a big one. We've generated electricity with steam boilers, spinning turbines, and three-phase AC generators powered by burning coal, all emanating from a central location, the power plant, to the minions who use it. We've been doing it this way for well over 130 years. The grid we use to distribute this power is also a cobbled-together amalgam of Band-Aids and duct tape. Of all the developed countries, the U.S. leads the world in electrical power downtime, brownouts, and blackouts, mostly due to an antiquated and inefficient grid. Look up the grid synchronization problem. Too deep to go into now, but that will explain a lot of the recent problems in Texas and why it's currently difficult to share power between electrical systems around the country. That also has a solution we'll chat about later. The grid, Actually, there's 3 U.S. grids: the East, the West, and lastly, Texas. And none of them share any capacity, which is part of the problem. Anyway, the grid uses AC technology from the late 1800s. The wires and switching systems in the U.S. power grid, claimed to be the most complex machine on earth, was invented by Thomas Alva Edison and George Westinghouse. You remember them? Again, 19th century technology. Until recently, there weren't many alternatives to generating and moving electricity. But as the march of progress moves ever rapidly forward, we have, in the last 20 years or so, developed alternatives. Economics. Fossil fuel companies, oil, coal, gas, have all made obscenely enormous amounts of money from a small handful of investors for the last 100 years or so of doing business as usual. Privatize the profits, socialize the risks. China built its booming industrial economy on coal. Why is China so driven to become an all-renewable energy-powered economy? With renewable energy, the fuel is free. One just has to figure out technologically how to redesign and fabricate efficient systems to make the harvesting and distribution of that free energy inexpensive enough for general use throughout the world. Remember, how can fossil fuels possibly compete with an energy generation strategy where the fuel is free in perpetuity? If the sun starts to run out, we all have much bigger problems to worry about. The first economies that derive a major portion of their energy from free sunlight and wind will have the most robust and thriving economies on the planet. With cheap and abundant energy, a society can do most anything at a huge economic advantage over their competitors. Transition from one energy system to more sustainable methods. The human race is facing a major confluence of disruptive technologies, meaning out with the old and in with the new, employing more efficient, economical, and sustainable methods well on into the future. I can ramble on and on about how bad and unsustainable fossil fuels are, but I won't. We all know it. Don't fool yourselves. The answer to many of our climate crisis technical issues and rapid transition will eventually be solved. It's inevitable. It's just a matter of how quickly it can be done and how much will it cost. Let's wind the mainspring of human progress forward. The thing to remember in all of this, which is rarely mentioned, is this fact. Once we've made the infrastructure transition from our antiquated system of generating and delivering electricity to the masses, we'll never go back. Let's look at the recent transition of the telecom industry. We used to send smoke signals, then telegraphs and Morse code. Then Alexander Graham Bell invented the telephone in the 1880s. Wires everywhere, party lines, switchboards, slow, cumbersome, and expensive, very difficult to maintain. That same system was ubiquitous for almost 100 years, up until the 1980s, when microelectronics, lasers, fiber optics, and satellites started to make its way into the telecom market. Do we still use a wooden box on the wall with a crank and a copper wire to the town switchboard? No. The solid-state silicon revolution, technology-driven primarily by the relatively modern computer industry, pushed the technology of material science and thin films to allow us to fabricate the most amazing devices, virtually changing our entire communication system in a very short time. The same is happening to the way we generate and use our electricity. Wind and solar are an energy source where the fuel is not just inexpensive, it's free, forever, no price volatility. Just like the telecom industry went through a 25-year transition, the electric systems of the world are now in that same transitional period. Technological solutions for moving electrons. Hydrogen-based energy systems. Hydrogen is an excellent method of storing electricity, but only recently have the technologies begun to be scaled to meet the demands of a modern energy grid infrastructure. Again, the thin film industry will be instrumental in pushing this to the mainstream, as fuel cells, which make electricity from hydrogen and air, and electrolyzers, which make hydrogen from water using electricity, all use thin film technologies to fabricate the membranes used for electrochemical water splitting processes in fuel cells. These use specially designed proton exchange membranes, PEMs, with many thin film coatings. Lots of room for cost reductions in these membranes and materials used to make them. Currently, there's a lot of electrical generation capacity that virtually sits idle when demand for electricity is low. Nighttime, fair weather. That's expensive, redundant, and inefficient. The plan is to use this excess capacity to separate hydrogen from water, thereby efficiently using the generation capacity and storing of energy for use when demand is high. Wind and solar. A little info on wind power. Wind is just recycled solar, natural convection. Wind is really expensive to produce per watt. We've all seen wind turbines in the distance, towering over the landscape. Today, one of the major innovations is the ability to build wind turbines that can stand alone in the ocean, known as offshore wind, taking advantage of much better and more consistent wind resources. There is a band off the northeast coast of the U.S., from Maine to North Carolina, that if tapped, could produce all of the electricity for the entire U.S. with much to spare. Modern wind turbines. Taller is better. Fact, double the height, triple the power. The majority of the turbines seen in Iowa and Texas and elsewhere, second-generation technology, are all about 300 to 400 feet tall and have a capacity of about 2 or 3 megawatts of output. Today, GE's latest version of offshore wind turbines are almost 1,000 foot tall and can generate 14 megawatts of power, almost 5 times the power for only 2 times the machine cost. Great Britain has ordered 45 of these to be installed north of Great Britain in the North Sea, which will provide about 10% of all of Great Britain's power, with an option for more. They want at least 45% of all electricity to come from wind by 2030, with more into the future. Solar photovoltaics, PV. About 50 years ago, someone figured out that sunlight can produce free electrons within a wafer of germanium, then silicon. Figuring out how to build a device that can harvest those solar-generated electrons was on. Wherever there is sunlight, there can now be power. The first silicon solar cells were manufactured for toys and transistor radios in the 60s because they were so inefficient and way too expensive for practical purposes. Then a funny thing happened in the 60s. The military said, quote, "We need these for space satellites of the future," at hundreds of dollars a watt. But just as Moore's law predicted the doubling of IC chip manufacturing processes and subsequent decreases in cost, the solar business has had similar improvements. Fast forward almost 50 years. Today, that silicon solar module on a roof or a solar field is without a doubt the cheapest way to make electricity by a long shot. As the PV industry grew in the 90s, primarily here in the US, the use of PV technology expanded. Companies started to make money, the market grew, the technology got cheaper, and the whole cycle continues today, where a solar module today costs less than 10 cents a watt to manufacture. Economies of scale have driven the price of a solar module to commodity pricing, where everything else, the wiring, inverters, storage, transmission, the so-called balance of systems, are now the major cost in a PV installation. Silicon has sort of a dirty little secret. Silicon has to be refined from quartz rock, or SiO2. Silicon doesn't exist as elemental silicon in the Earth's crust, even though it is the second most abundant element in the Earth's crust at about 28%, with the remainder being mostly oxygen, SiO2. So the high temperature carbothermic reduction process at about 1600 degrees C uses carbon or coke to remove the oxygen, forming CO2 in the process. So there's quite a bit of CO2 from the silicon refining process alone. Plus, all of the electricity used in heating and processing silicon results in not insignificant carbon emissions. China alone makes almost 1 million tons of silicon a year. That's a lot of coal-fired electricity and resulting CO2. Reducing the carbon footprint of the electricity going into refining the silicon can reduce the CO2 footprint of silicon solar cell manufacturing. Thin film PV technologies require significantly less raw materials and refined materials. At some point, the demand for even cheaper solar modules and balance of system components will necessitate a thin film solution, one that uses significantly less processing and semiconductor materials that can be manufactured at huge industrial scales. NREL pioneered solar research back in the late 70s, concentrating on thin film technologies. The first wave of PV manufacturing, both silicon and thin films in the 70s and 80s and early 90s, were all focused here in the US. The push for a thin film solution and even lower cost, lower carbon footprint is still on. Other thin film technologies soon followed that slowly but surely approached silicon in cost and efficiency. The most successful thin film company today is First Solar, a phoenix which rose in the early 1990s from the ashes of GlassTech Solar, one of the earliest amorphous silicon-based thin film PV startups that never panned out. I know, I worked for them in the late 80s. First Solar uses a thin film of cad telluride, an alloy of cadmium and tellurium, a byproduct of copper mining. Cadmium and tellurium sublime at about 800 degrees C, so they are able to be turned into a hot vapor and transported to the substrate surface. Today, First Solar can produce a monolithically manufactured solar module using giant inline vacuum chambers and a technology known as VTD, or vapor transport deposition, depositing a 5 to 6 micron film of cad telluride onto large 4-foot by 8-foot sheets of glass, also coated with a thin film of transparent conducting oxide, or TCO, usually fluorinated tin oxide, via thermal CVD or sputtering. Multi-gigawatts of yearly production with large economies of scale make First Solar modules very cost competitive with the best silicon solar modules produced today. Reducing the carbon footprint of solar. Today, crystalline silicon PV is mostly produced in China with very low cost, although it's government subsidized, low cost labor, and 70% of their electricity still produced from coal, adding to the carbon footprint. So when China and their 1.3 billion people have made the transition to a mostly renewable energy supply, they'll have the most robust economy on the planet, a competitive advantage over the US, unless we also do the same in the same time frame. The longer we wait, the more it's going to cost us all. The Chinese government has invested almost $2 trillion on its renewable energy infrastructure and manufacturing capabilities over the last 15 years. No wonder they dominate the market. Let's talk about the new kid on the block, showing a great amount of promise. Perovskite thin films. That's a hot topic today. The word perovskite is a Russian word describing a specific crystallographic orientation of atoms within an organic molecule. The current material that shows great promise is methylammonium lead iodide, a compound made up of various liquid metal organic chemical precursors. This material was discovered as a photovoltaic material less than 10 years ago and is capable of making solar cells and modules with comparable performance as the best crystalline silicon modules today, over 22% efficiency. By putting this technology on top of standard silicon solar cells, a tandem cell, which can raise the efficiency to over 25 to 26% by having two solar cells, one on top of the other, each grabbing a different and broader part of the solar spectrum. It's estimated that only about 35 kilograms of perovskite precursor will be needed per megawatt of generation capacity, compared to 7 tons per megawatt for silicon. Perovskites don't require all the high temperature processing steps over 1450 C for silicon and can be deposited using blade coating or high volume roll-to-roll manufacturing processing, a forte of the thin film coatings industry. Balance of systems, transmission and storage. Everyone talks about wind turbines and solar farms as being the solution, but just as it doesn't make economic sense to convert your 1965 VW Bug into an electric vehicle, as the original VW Bug was never designed to be an electric vehicle. Today, our electricity grid will also need a major upgrade to modern technologies. We can send an email almost anywhere around the world in an instant by sending electrons over our high-speed telecom backbone so that it arrives to you in fractions of a second, essentially traveling at the speed of light. The grid needs to work the same way. The need for baseload systems is only necessary when you have an inefficient and antiquated grid system. Remember, there are 128,000 terawatts of available power from the sun hitting the earth at any given moment. All we need is the ability to capture about 18 terawatts of that to power the entire human civilization. But we need to move it from where it's generated to where it's needed worldwide. China's Three Gorges Dam rectifies about 6 gigawatts of power from giant hydro-powered turbines, the equivalent of 6 large nuclear power plants, and sends all this power via long-distance, high-voltage DC, HVDC, transmission lines to Shanghai and Beijing and other industrial areas of China. High-voltage DC is easier to transmit, as once the power arrives where it's needed, it is reconverted back into AC power for the local grid, eliminating the three-phase synchronization problems with our existing all-AC grid technology. Smaller, more interconnected, localized and regional grid systems can benefit from the rapid advancement of high-capacity storage solutions. We need a way of leveling the loads from hot days to cold days, dark to light, high demand to low demand. Today, in many places, the cost per watt of solar and storage is coming in at lower cost than natural gas generation alone, and that is without factoring in the climate cost of burning natural gas. The hidden cost. Fossil fuels will continue to increase in price as charges for emitting any carbon will be added to the base cost, whereas renewable energy just keeps getting less and less expensive by pushing the technology advancement. Solid-state electronics, for one, have now made it practical to move and distribute electricity the same way we move information. Today, data is transmitted around the world at the speed of light via solid-state electronics. The thin film technologies that made that possible, CVD, sputtering, evaporation, etc., were all originally developed for low-power applications like microelectronics. Today, that same solid-state technology, only now evolved for high-power electronics, allows us to send and receive electricity at gigawatt scale over DC lines instantaneously. What was once impossible is now possible, and without a doubt is the most economic method of moving into the future. A major upgrade and re-engineering of the electricity grid will be necessary to replace our inadequate and antiquated system. Storage. One of the great misbeliefs about solar and wind is that you can't store it. It's no longer true. In addition to the recent explosion in reliance on low-cost, high-energy density, lightweight batteries in our everyday lives, which were really developed to power our computers, phones, and iPads, have led to the automotive industry transitioning to batteries and will only continue to drive the technology to mainstream proportions. Giant high-tech battery farms are cropping up to store grid-scale power for hours and days on end, used for load leveling and balancing. The U.S. Department of Energy has the Electrons to Molecules program, doling out money for R&D on sunlight to gaseous or liquid high-density fuels to economically replace the need for fossil-based fuels. The revolution in solid-state battery technology is remarkable, and as with solar and wind, rapidly dropping in price and crossing the price point Rubicon. These are all using thin-film technologies such as ALD and others to enhance many of the materials going into modern battery storage systems. Hydrogen, as we talked about earlier, is an excellent method of storing electricity, but only recently have the technology begun to be scaled to meet the demand of a modern energy grid infrastructure. Again, the thin film industry will be instrumental in pushing this to the mainstream as fuel cells and electrolyzers, which make hydrogen from water using electricity, use thin film technologies to fabricate the specialized membranes used for electrochemical processes. Modern thyristor-based switching has virtually eliminated the synchronization problems, allowing the instantaneous transmission of high voltage DC transmission over long distances so that sharing of power over major grids or even worldwide is now possible and economically viable. Localized distributed power networks working very similar to internet nodes will keep the local grid network balanced. Remember, how can fossil fuels compete with an energy generation strategy where the fuel is free in perpetuity? If the sun starts to run out, we all have much bigger problems. Politics and ideology no longer drive the argument. Economics do. Public utilities have a fiduciary responsibility to deliver electricity to you, the customer, from the least expensive sources available. That is wind and solar. Conclusion. There are no easy fixes to the environmental, economic, and social problems of the world. But continued research and development, along with governmental policies to enable rapid deployment of these advanced technologies, funded by both government and private investment dollars, will continue to push the technology towards cheaper, better, and faster, modern and carbon-free energy world. There are many and unique solutions out there, and many of them will come from the thin film industry, since this industry already touches so many of our daily lives. Opportunities abound. I want to thank the SVC for the opportunity to give this talk on sustainability. We all need to know this information, even though it sometimes contains information we don't want to hear. Thank you very much.